In this video, we are going to talk about GANs, or Generative Adversarial Networks. Recently, I've made videos on diffusion models, so I thought to start covering this space of generative models as well. And for this one, I'll be going through the first paper, which introduced GANs. I'll cover the intuition behind it, different components that are involved, and how to train them, get into what its objective is trying to achieve, and go over the convergence proofs that the authors put forth in the paper. Lastly, we'll see how to implement and train it on the simple MNIST dataset and check out the results of doing that. So let's get started. The end goal of GAN is pretty much similar to any generative model. We have some complex distribution and a set of samples coming from it, which is our dataset, and we want to be able to generate data from this distribution. Specifically, we want to learn how to convert samples from a very simple distribution, let's say a normal distribution, into samples which seem as if they are coming from this complex distribution. And if we are successful in doing that, then we are not limited by the number of data that we had at the beginning. We can generate that at will, whether the distribution be in the space of images, text, or speech. Let's focus for now on the goal of being able to generate handwritten digits in white on black background. We assume that in the space of all images, there exists some distribution which has high probability for all images that are handwritten digits, and zero probability for all images that are not handwritten digits. And we are interested in having a model learn to capture this distribution because we don't know how to express it or what its parameters are. Because if we could do that, then we can anyway generate samples at will, like we can for a Gaussian distribution. GAN comprises of two models: a generator, which is responsible for taking in samples from our normal distribution and converting them into samples from that complex distribution. Assume the generator takes in our normal distribution and generates some samples. Let's call the distribution of these generated samples as predicted distribution. Here we have the original data distribution in white and predicted distribution in blue. If we could find some measure of distance between these two distributions, then we could train the generator model with this distance as loss. And ultimately, this would lead to the generated samples matching closely to the data distribution. And this is exactly what we do in variational autoencoders, where we use the KL divergence loss for the prior distribution predicted by the encoder, and try to force that to be as close to normal distribution as possible. But here in GAN, we do something different. We instead have another model called a discriminator. The responsibility of discriminator is to take in samples from the data distribution and predicted distribution, which are samples from generator, and learn to distinguish them into which sample is coming from the data distribution or real, and which sample is generated or fake. The generator, instead of being trained on some distance measure between distributions, is now trained on the measure of how well the discriminator is able to distinguish the data samples from the generated samples. Its goal is to be better at fooling the discriminator into believing that its generated samples are in fact real. And like mentioned before, discriminator's goal is to be better at identifying which sample is real and which is generated. These two models become each other's adversaries, as their goals are exactly the opposite of each other. And in order to keep improving, they need to keep becoming better than each other. Hence the name Generative Adversarial Networks. Because they are continuously trying to beat each other in this game and thereby improving, what happens is that initially, the generator outputs samples which the discriminator can easily learn to recognize as fake. But with this feedback, the generator improves and starts generating better samples. The discriminator also meanwhile improves and starts to learn to recognize even these better samples as fake, and still classifying the original data samples as real. With time, the generator keeps on getting better and better, and ultimately ends up generating samples that look exactly as if coming from the original data distribution. And all the discriminator can do then is predict at random which is real and which is fake, like tossing a coin, because they are completely indistinguishable. And then we would have achieved our goal of generator being able to output samples as if they are coming from the data distribution. So we have seen the components. Let's now get into how do we train both these models. The authors of the paper use this value function to optimize them. The discriminator improves by continuously trying to maximize this, and the generator improves by trying to minimize this, again acting as each other's adversaries in this min-max game. Thinking in terms of iterations, starting from random initializations, we update the discriminator by maximizing this objective. Then, with the updated discriminator, the generator tries to minimize this objective. With this updated generator, the discriminator again tries to maximize this objective. And this keeps on repeating. Rather than trying to dissect this objective, let's see what is happening if we just train these models on the classification objectives that they have. And that will give us a better understanding of this objective and how to implement it. First, we look at the discriminator, which is trying to learn how to classify the input images as real or fake. We could turn this into a binary classification task, with the real images as ground truth label 1 and fake images having ground truth label as 0. And the network could predict the probability that it thinks that the given image is real. Let's say it generates these predictions. Then we could use binary cross entropy loss to train this discriminator with these labels and predictions. So this is the binary cross entropy loss, with yi being the ground truth labels, either 1 or 0 as per our setup, and pi being the prediction by the classification model for the ith input, which is nothing but the output of our discriminator for that ith image. Now, since the label yi would be 1 for real images, so for real images only the first term will remain and the second will vanish, because 1 minus yi will be 0. And similarly for fake images, only the second term would remain as yi will be 0. So we can express this as this, where xi is an instance of real image and zi is a random noise sample. And g of zi is the fake image that the generator returns for this sample. In order to make our classifier better, we minimize this loss. So we can achieve the same thing by maximizing the negative of this loss. And this is now exactly what our objective also does, except the difference of sum replaced by expectation. And that's because we never have access to the entire distribution. We only have access to a certain number of samples from this data distribution. 60,000 samples in the case of MNIST. And if we assume that the sampling process is according to the probability distribution, then training with the objective the authors mention and training with the cross entropy loss would be the same. So for the discriminator, we would simply be training it to give higher probabilities for real images and lower probabilities for fake images. For the generator, we could leave at saying that since the generator is the adversary of discriminator, we must train it with the opposite objective. And since discriminator maximizes this, generator must minimize this quantity. But from the same classification perspective, we can arrive at this formulation as well. Generator wants to minimize the probability that discriminator thinks that the generated sample is fake. If we would have to improve the discriminator, we would have minimized the binary cross entropy loss between fake label and the generated sample. So for improving the generator, we can maximize this, or we can minimize the negative of this. And this quantity is same as the negative of BCE for fake images and label 0. And the first quantity is doing nothing here because as far as optimizing generator is concerned, this is constant. So all this min-max objective does behind the scenes is attain the classification objectives for both the discriminator as well as the generator model. Now we said that for generator, we want to minimize this objective. And we saw that this is equivalent to maximizing the BCE with 0 label for the discriminator output on generated sample. When you plot the log of 1 minus x graph, you will see that in regions where the discriminator gives lower probabilities, the gradient is very small in terms of absolute value. But at the start of this game, the discriminator will indeed give very low probabilities for fake images, because it will easily learn to distinguish between real images and the fake nonsensical samples. And this is actually when the generator will need to improve using the gradient of this loss. But that becomes an issue because of the weaker gradients in this region. The authors instead optimize using the log of x function. Two things to note regarding this. First, minimizing log of 1 minus x is same as maximizing log of x in the 0 to 1 range, which is what we are working with here. And second, the gradient for the initial iterations where discriminator gives lower probability to the generated sample is now much stronger and of higher absolute value. Hence, it's better to have the generator, instead of minimize this value, maximize this value. This is again exactly same as minimizing BCE, but with label 1 for the discriminator output on generated sample. So ultimately, instead of trying to minimize the likelihood of discriminator predicting the generated sample as fake, we are trying to maximize the likelihood of discriminator predicting the generated sample as real. For training these models, instead of jointly training them, it's more stable to train them separately in iterations. From an implementation perspective, we do this by having different optimizers for generator and discriminator, each one catering to its respective model parameters. So for discriminator, we'll get a random noise sample and feed it to the generator to get the fake image and fetch a real image sample from the dataset. Discriminator would be trained with two losses, cross entropy for real image with label 1, and second would be cross entropy for fake image with label 0. We would backpropagate and update the parameters of discriminator, and we'll ensure that the backprop stops right here and does not go all the way to the generator because it's not needed. For generator, the dataset is not in the picture, and all we do is take a generated sample, feed it to the discriminator, and this time have loss as this, like we saw, cross entropy between the generated image and a real label. We backprop all the way down till the generator, but we only update the generator and the discriminator parameters remain as it is. The authors also mentioned the training algorithm in the paper, which is pretty much similar to what we saw. These steps are used to optimize the discriminator, and just like we saw, taking in a real and fake sample and update it using our loss. Though the authors mentioned to repeat the optimization step of discriminator for k steps, but in experiments, they use k equals 1. For generator optimization, we have these steps. And again, rather than minimizing this, we maximize this objective. The authors also proved the optimal point of this min-max game, and we'll go through that before moving on to implementation. Intuitively, we can see that what we desire is that the generated sample be exactly same as the real samples. But when that happens, the discriminator will be confused because it can't distinguish between them. So it will end up randomly deciding which is real and which is fake and have 0.5 as the prediction probabilities. Now let's see if optimizing the GAN objective allows us to reach there. We'll first try to find the optimal discriminator. When we take samples Z from the normal distribution P of Z and feed it to the generator, it will return an image. Let's call it G of Z. Continuing this process for the entire distribution of noise samples will give us a distribution of images in the image space. Let's call this P of G. Generated images that are mappings of highly probable Z's in the normal distribution will have high probabilities in this P of G distribution. Going back to the expression, now we can replace this term with this. All we are doing here is changing the random variable from Z to G of Z. And hence for computing the expectation, instead of using P of Z, we are using the distribution of this new variable, which is the distribution that we get by passing noise sample Z through the generator, which we have termed as P of G. Then rewriting the expectation gives us this. In this expression, it might seem that these x's are different. At least to me, it did initially, and hence we can't really combine them. But think of this x as being points in the image space. A subset of these will be handwritten images, and similarly, even the generated images, no matter how nonsensical they are initially, they are still a valid image, and hence correspond to some point in the image space. So with the notion of x being points in the image space, we can combine these two. Now for the optimal discriminator, we just maximize the term inside the integral. This is similar to optimizing this expression, and after finding its derivative and equating it to 0, we'll get this. This tells us that the optimal discriminator for a given point x in image space will predict the probability of it being real as p data of x divided by p data of x plus pg of x. So given a particular state of generator, we'll get a specific pg distribution capturing images produced by generator. And here you can see that for samples that have p data as 0, so nonsensical images that a randomly initialized generator produces, dx will be 0, meaning that the optimal discriminator will learn to recognize them as clear fakes. For samples which have p data much higher than pg, so samples in dataset which the generator has not yet learned to produce, dx will be 1, meaning the optimal discriminator will learn to recognize them as real images. And for samples that are equally likely in p data and pg, meaning the generator outputs that look exactly like handwritten digits in our dataset, the best the optimal discriminator can do is randomly choose, as dx will be 1 by 2. Okay, now given this is what the optimal discriminator is, let's see what we get by trying to find the optimal generator once the discriminator is the optimal one. So given this optimal discriminator d star, which we found to be this, the generator will try to minimize this objective, where again we have rewritten the expectation. To this we add and subtract log 4. And why do we do that? Because when we put pg equals p data in this expression, utilizing the optimal value of d star x, we get minus log 4. Obviously, we can add and subtract anything. But because minus log 4 is a possible minimum value, since the best the generator can do is completely mimic p data, our hope is that we'll end up with minus log 4 plus something which will tell us about the optimal point of this minimization objective of generator. We can rewrite log 4 as 2 log 2 and then can rewrite these log 2 terms as this, because after all, both are probability distributions and will integrate to 1. We then bring them inside the respective integrals to get this expression, minus log 4 plus 2 KL divergence terms, both of which will be greater than or equal to 0. The authors rewrite this expression as this, where for the purpose of this video, all we really need to know that this is twice of Jensen-Shannon divergence metric between p data and pg, and it is another measure of how dissimilar two distributions are. And twice of this metric is exactly equal to the quantity that we had above. Moreover, its lowest value is 0 when pg equals p data. So now we can see that the minimum point of this objective, which is minus log 4, is indeed when pg equals p data. Hence, our optimal generator, which we get by minimizing this objective till its global minima, will end up mimicking the data distribution through its generated outputs. And our optimal discriminator, which was this, with pg equals p data, it will end up predicting for any image x, be it real or fake, a value of 0.5, because it won't be able to distinguish. This is exactly same as what we had thought intuitively. Generator ends up generating same kind of data as real samples, and discriminator has to resort to deciding randomly which is real and which is fake. Next, we'll implement a simple GAN with FC layers and see how all of these optimizations that we talked about looks in code and see some results for training it. I'll put the entire code apart from the dataset class in this one file because it's simple and easy to follow that way. I first define certain constants which will be used. Latent dimension is the dimension of noise sample that we'll use, which here I set as 64. So my generator will get a 64-dimensional noise vector as input. Our images are 28 cross 28 with single channel. Samples and rows fields will only be used for visualizing what the generator is outputting every certain number of steps. Our generator will be taking in samples of size latent dimension and progressively convert it into a vector of 784 dimensions, which will represent our 28 cross 28 image. These will be the dimension of those layers. This self-taught layers will be a list of layers where each one is an FC layer followed by batch norm and activation. And for activation, I am using leaky ReLU. For my dataset, I scale the MNIST images to be from -1 to 1, which is why for my last FC layer, I use tan H as the activation to have images generate within the same scale. And the last layer also has no normalization. In the forward method, after calling those layers one after the other on the input noise sample, which would be batch size cross 64 dimension, I reshape the output to be batch size cross channels cross 28 cross 28. The discriminator would be taking an image and return one value for each image, which will be the probability that it thinks this image is real. Our discriminator is also similar with FC layers, which will convert the 28 cross 28 image all the way down to 1. The FC layers are followed by normalization and activation. However, instead of batch norm, I used layer norm, primarily because that performed better, but intuitively because the discriminator would receive batches where images could either be real or fake, which will not really look alike, and their statistics would also be different, as they are coming from different distributions. Moreover, the generated samples distribution would also keep on changing. So normalizing based on batch statistics, which will continuously change, might not be as beneficial as it is for the other problems. There are some tricks which we can do to remedy this, and in future videos we'll see how to do that, but for now I used layer norm instead and it worked better. I have not used sigmoid activation in the last layer because I'll use BCE with logits loss. In the forward method, we first flatten the input and then pass it through these linear layers. And finally, the discriminator returns an output of shape batch size cross 1. This train function would encapsulate our entire training logic. The dataset class here just takes in the images from the directory and converts them to a tensor and scales them from -1 to 1 range. We then instantiate the generator and the discriminator models. We have two different optimizers for generator and discriminator, and for both, I use Adam. But if you notice, I use 0.5 as the momentum parameter rather than the default 0.9. This is something I tried only because it's mentioned in the DCGAN paper, and it turned out to perform much better. But again, knowing that it performs better, an intuitive reason could be that the distribution of samples which the generator needs to generate and what the discriminator needs to successfully classify will keep changing as the game progresses. So maybe that's why a high momentum value might not end up being that conducive. For each of the epochs, we'll perform the following steps. We get our image samples from the dataset and first optimize the discriminator. Remember, for discriminator, we want to correctly classify real images as real and generated samples as fake. And we don't want to compute the gradients all the way for generator. So let's do that in code. We have the generator generate a batch of fake samples by feeding it samples from the normal distribution. The labels for real images are 1 and that for fake samples are 0. And for the fake samples, we ensure to detach before passing it to the discriminator so that the gradients are not computed for the generator. We use binary cross entropy loss to get the loss for fake and real image, average them, and update the discriminator parameters using that loss. Now on to optimizing the generator, for which our goal is to maximize the likelihood of discriminator classifying a fake image as real. And we want to update the parameters of generator but leave the discriminator as it is. We pass the fake samples to discriminator, but this time compute the loss with labels as 1 because that is the likelihood that we want to maximize. Only the generator gets updated here because this optimizer was instantiated with only generator parameters. This is it for the core training logic. And all we are doing now is just saving samples every 50 steps by calling this info function, which I'll define later. For the infer function, we generate samples from the generator and scale it back to 0 to 1 range. Remember, because our generator returns images in the scale of -1 to 1. And after that, we just save it. Once you train this for about 30 epochs, you get the following results. For getting colored images, you can just replicate the grayscale MNIST images to 3 channels and then randomly multiply each of them with a different value. I would say that the results are decent, considering this was just a GAN with FC layers. And definitely some of the images are more perceptual and less blurry than what you would get from a VAE. So this was all that I wanted to talk about in this video. We went over how GANs work, its components, and how to train them. We dived deep into its objective, and in the end saw how one can implement a simple FC layer GAN. In the next videos of GANs, I'll cover research works published after this initial GAN paper, and progressively reach to the latest papers on it. Thank you so much for watching this one, and I hope you found this helpful. See you in the next video.